We've done so many codes. We've done the what's called this, the numeric codes. We've looked at the weighted numeric codes. We've looked at what the numeric code that was not weighted. We've so far looked at what at exercise 3. Now we are going to look at what we call the gray code. Very nice code. The best code we have so far for what? Until someone comes up with something better, it is the best code we have for counters. The gray code. Okay. A lot of our designing, when you design circuits, you're going to see that the gray code is going to be preferred. You're going to be using the gray code so a lot. So you need to understand the gray code. Now, this is beautiful. Why? Because it is a unit distance code. This is a unit step or distance code. What do we mean? This is one code where in counting, when you move from one count to the next, when you move from one number to the next in our normal counting, normally with what it would only allow a change of what of one digit at a time. Let's look at a scenario where we have a number. We are transitioning from a 4-bit number 0 1 1 1, which we know is 7 in what is 0 1 1 is binary for what, for 7. And then let's say we're moving on to the next count. The next count is 8, but 8 is what happens here? The 0 changes to a 1. All the ones change. All the ones change to what? To zeros. So all 4 bits are changing. This is also possible when you're looking at any number. Let's say we're living from 1 1 1 1 1, which is what? Which is 1 2 3 4 5 6 7 bits. And we are moving to the very next number. In the normal count, we will know that it will be 1. This 7 will now transform to zeros. 1 2 3 4 5 6 and 7. So this is how many bits would change actually depends on what it actually depends on what on the number of bits we are dealing with. So you have a random scenario where now all these numbers, all these lines are changing. Remember, these are on and off lines. And now all these lines are changing what and all you're doing is changing by one count. You are moving from this is only one extra than that. Now there's a possibility that anything would happen if any of the digits was to be faster. Let's suppose that digit was faster and there was a reader that would translate this. It could actually give us a wayward number, an awkward number. Okay, let's say all the change, let's say that bit was faster in changing. We've got a funny number. Let's say all of them have got different. We could have a really disastrous scenario where we have got so many fake counts in between before we move from our count to the next count. So to avoid that, we came up with the unit distance code, which will only allow one change per time. Let's look at the gray code and saying, let's take 4 bits because we started with 4 bits. Let's have our binary. We are just counting our binary. Oh, okay. Since I'm counting, I'm going to start with my decimal because this is our language. Then we're going to see what it is in binary. Then we're going to move to gray code and see what the changes are. Now, 0, we're doing just the decimal count. We're not going to go beyond decimal, even though the normal counts go beyond that. I mean, obviously. But I want to just use this. Let's say we're having a decimal counter. And then this is 7, this is 8, and this is 9. Now, in binary, let's say we're using 4 bits because we need to have 9. So that will be 0, 0, everything. That will be 1. That will be 2. That will be 2 and 1. That will be 4. That will be 4 and 1. That will be, where am I? Oh, 4 and 2. That will be 4 2 1. That will be 8 1 1 0 0, and that will be only the 8, and that will be the 8 and the 1. Now, if we look here, we are happy. There's a unit distance between 0 and 1, only 1 bit changed. Moving right to the next count, what has happened? This bit has to change to 1, that bit has to change back to a 0. So 2 are changing. So this is not unit distance. So this is not unit distance. Now going back there, we are happy. What do we do? Is unit distance, only this bit changed. Okay. Coming here, now we are very unhappy. This is all 3 bits are changing. Okay. Coming there, only 1 changes. Here again is 2 bits changing. We are unhappy. Coming there, it's only 1 change. That was 1 change. This 1 change, we are happy. Here, there is a problem. We've got so many bits changing. Actually, we've got the most bits changing in that situation. So we want to avoid a scenario like that. We don't want that disastrous occurrence where we find, because why? These are physical circuits that are actually having what? That are actually having that are actually wired. These circuits are normally wired, and then probably they'll be wired to displays and whatever. Probably they'll be wired to other circuits where they're supposed to send certain messages and whatever. So every time that bits don't change, that don't change timelessly, and they probably some are faster than others, we can have fake counts. Look at this scenario, for instance. Let's suppose this one was fastest to change. We would have a scenario where we have 0, or I mean to say, let's say this was the fastest. Before we go to 8, we will have 0, 1. Because this is the fastest, it changes to a 0 there and 1. And this 5 is red for that instant, that the other bits are still changing. For other circuits or sensitive circuits, that could be actually a serious issue. So what do? We rearrange the count. All we do is rearrange the count. What do? We say, okay, we are happy with that first count. Okay, we are happy with the what unit change here. Okay, we are not happy with that change there. What do? Okay, we say we rather jump the 2 because it was going to give us 2 changes. We rather jump the 2. Okay, we say then all we're doing is rearranging the count. We go back to the 2. So all we do is we skip to the 3 because it allowed us to what? To only have one unit distance, only 1 bit changing, and then we came back to the 2 because now we are trying to avoid. So what do we do now? When you get to 2, we're trying to avoid multiple changes so that we avoid these race conditions. So now we say, okay, what about this one here? We say, look at that. We skip all the way to that. Why? Because we are trying to have 1 change. Any other count would have had more than 1 change. If you look, we could have gone to 5, but we would have had to change this. We have had to change that. We have had to change this. So no, we skip to 1. That would give us only 1 change. We come here, we say, okay, we go back because this one allows us to. So we skip to what is supposed to be 7, just because we're trying to accommodate what? We're trying to accommodate 1 unit distance. All right. When you come to this one here, we say, okay, we are happy, and we say, because we only change, we are going back to our counts. That will not make that will not have us have more than 1 bit being altered, being changed. All right, to avoid again the race condition. So now we say, okay, what about this one? All you do is change something back to accommodate the previous counts. We don't want to totally leave them, so we keep going back to the previous counts. We go up, making sure we have 1 change at a time. Where we can, we go back if it allows us to what? To have only 1 change. So then you say, okay, from there we say, okay, now we are going from what? From 7 to 8. What do? We say we only change that bit there. Then we come and you say we have only changed and then we've only changed that bit there. What have we done? We've actually even skipped some counts here. So if we were to continue, we are already, what is supposed to be 12? We've done it already. We are doing 12 before 11. What do we do? Let's say we had 10. That 10 would have been 1 0 1 0, but here we would have only 1 unit, 1 distance change. All right, so we'll rather change this back, okay, and go to what looks like a what? Like a 15. Okay, all right. So we say if we had to go on and go to 11, that would have been 1 0 1 1 what do? We say, okay, we are happy here, we are happy there, we are happy there, we are changing down. So we are counting down. Let's go to 14, and it would have been 1, 11, yeah, 12. What am I doing? I'm supposed to be at 12, not 14. 12. I'm curving a little bit. 12 would have been 1, 1, 0, 0, but we instead say 1, 0, 1, 0. We are changing back to accommodate. Let's say 13. 13 would have been 1, 1, 0, 1. What do you see here? This would have been 1, 0, 1, 1. We change 1. Okay, we only change 1 bit. 14 would have been 1. Oh, okay, 4 bits and you can count up to 15 anyway. So we'll have up to 15. 14 would have been 1, 1, 0, and here it's going to be 1, 0, 0. Back to 9. Now, because we only changed 1, now we say 1, 1, 1, 1 is going to be 1. And now, suddenly, 8, that was so many counts away, is suddenly. What do we see? We only changed this one. We came here, we only changed this one. We came here, we changed that one back. We came here, we changed this one. We came here, we changed that one. We came here, we changed this one back. We came here, we changed this one back. We came here, we only changed that one. We came here, we only changed this one. We came here, we only changed that one. We came here, we changed this one back. We came here, we changed this one back. We came here, we changed that one. We came here, we changed that one back. We came there, we changed that one back. So we've done our normal count 0 up to 15 with the 4 bits, which is what it should do. But all we've done is rearrange the count so that each time we have what? We have one unit distance. Why? So that there is no race condition. When we're doing our counters, we don't get fake readings in between. All right. But how do you convert from binary to decimal? Let's take the first one, 0, 0, 0, 0. Obviously, that one there. What do? We take the first one as it is, 0. Now we add 0 to the next one. It is 0. We add that 0 to the next one. It is 0. We add that 0 to the next one, and it is 0. Okay. So what do? We are adding implicitly. We are adding within, okay, the binary number. So how do we move from 0, 1, 0, 1 to this number? We take the first one as it is. We lay it down. We add within that one to that one. Okay, implicitly that will be a 1. That one, 1 to that 0, that will be another 1. That 0 to that 1, that will be a 1. That's how we got here. Take a random case, 1, 0, 1, 0, 1, 1. First one, we lay it as it is. Then we add implicitly 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 0. We ignore the carries. Remember, sum is 0. Then it's carry 1. So we ignore the carries. That's how we got here. Okay. Finally, 1, 1, 1, 1. First one stays as it is. We add implicitly 1 plus 1, 0. Implicitly 1 plus 1 is 0. Implicitly 1 plus 1 is another 0. Okay, so when you are doing this, we add within the number. Okay, we add within the binary number to get our what? Our gray code. We are going to use this code a lot. We are going to, when we are doing counters, we are going to use not learning what the counters are, but when you are actually doing the design of the counters, we are going to use this code a lot. Now, this is us converting from what? From binary. So I can be, if you are given a number 17 and you are asked to convert it to gray code, it must obviously first go to what? You must first divide there by 2 to make it, to convert it to base 2, which will be 1, 0, 0, 0, 1. Then, because gray code can only be done from binary, so you are first going to go to binary. You are first going to go to, your first conversion is going to be go to binary, because gray code is worked out from what? From binary numbers. Now you have this, that is 1. Okay, 1 plus 0, that is 1. Then you are adding implicitly 0 plus 0, you are going to have what? 0. 0 plus 0 implicitly, you are going to have 0. 0 plus 1, you are going to have what? 1. Okay, that is what your equivalent of 17 is. What am I doing? That is what your equivalent of 17 is in what? In gray code. Okay, in gray code. So double check 1 plus 0 1 0 plus 0 0 0 plus 0 0 0 plus 1 1. Okay, that is how basically you. So if you are given any other base, you first have to go to what? Take it to binary, because gray code is only worked out from what? From binary. Now what I'm going to do is I'm going to do one last part. I'm going to take let me have, I use an eraser here. Okay, it's already there. I'm going to show on that little window there how we are going to move from what? From gray to binary. So let's suppose I have that number, I want to go there. I have 0 0 1 0 and it's gray, and I want to go back to what? To binary. Okay, to binary. What do? You add explicitly. I take my 0. Now I don't add implicitly. I don't add 0 to 0. I add my 0 to my previous answer. That's 0. Now I take, because I took 0 first, then I say 0 plus 0 is 0. Says this 0 plus 1 is 1. This 1 plus 0 is 0. Okay. No. This 1 plus 0 is 0. Okay. This 1 plus 0 is 1. Okay. This is my binary number. If you look, that is what it is. Look, if you look there, we placed the 0 first. Okay. Then we said 0 plus the next one, 0, that 0 plus the next one there gave us the second one, which is a 0. Okay. Then we say that 0 there plus the next one there, which is a 1, gave us a 1. Okay. Then that 1 plus the last 0 there gave us the last one there. Okay. So basically those lines are what we are doing here now. We are adding explicitly. We're adding implicitly. Now we're adding explicitly. Let's come and take that one there. 0 1. Why am I doing 0 and I'm writing? I'm doing the opposite. Am I tired or what? 0 1 0, and this is gray, and I want to convert this to binary, back to binary. What do? We know the first one is as it is. Then our answer is added to the next one is 0 plus 1. It's a 1. Our answer 1 is added to the next one. 0 1 plus 0 is 1. Our answer 1 plus the next 0 is a what? Is a 1. So there is our answer there in binary. Let's go ahead and check there. Our 70111. Now I will take two more examples. Let's say I take this one here. 1010 is in gray. It's in gray. So I want it in binary. What do I do? Explicitly, first one sits our answer plus the next one. 1 plus 0 is 0. That's explicitly the answer with the previous number. When we're converting from to gray, we're adding within the decimal number, the binary number. Okay. So now our answer with the next one, so it's number 2 answer, go to number 3. That plus 1, 0 plus 1 is a 1. Our answer is the third one, go to number 4. 1 plus 0 is a what? It's a 1. And this is what our binary number is. Where are we? Am I right here? Let me check. 1 plus 1 stays. 1 plus 0. Oh God, what have I been doing? I got wrong answers, that's why my answer is wrong. 1 plus 0 is a 1. Okay. Our answer 1 plus the next one is a 0. We're sleeping with the second one there. Our answer, third one, 0 plus the fourth one there is a 0. Okay. Is that correct? 1 plus 1, 0. 1 plus 0, 1. 0 plus 0, 0. Yes. So this is, yes, it came from that one there. Last one, last but not least, we have what? We have 1 0 0 0. I picked them at random. 1 0 0, we have this is gray. This is coming from gray. We are going to binary. What do we do explicitly? That one stays. 1 plus the next one is bit number 1 plus number 2 of the original. That's a 1. 1 plus the next one, 1 plus 0, it's a 1. 1 plus the next one is a 0, it's a 1. That is what it was in what? In binary. 1 plus 1, so 1. 1 plus 1, 0. 1 plus 1, 0. 1 plus 1, 0. Yes. When you come and check, yes, we are happy. So this is how we convert. I showed you previously how we convert from what? From binary to gray. Now I was showing how to convert from gray to binary. So I don't know what is the beauty of this one. The beauty is that it's got what? Single distance movement. It does not move. And when you go to the next count, it does not juggle so many switches. Okay, only one line is affected at a time. So it's a unit distance code or unit step code. So I hope that was marvelous. I hope we enjoyed it. Remember one last scenario, because I know people tend to forget this. So I'll deal with it. We have a binary number. Okay, to go to gray, what do? We add implicitly 1 plus 1 0, 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 1 plus 1 0. Okay, now this is our gray. To go back, what do? 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. Yes, number of bits cannot change. So now we're going back to what? Basically we are going back there, but let's see. This is us going back to binary. What do? First one stays. Now we add explicitly. We're implicit, we're within. Now we are moving explicitly. We take the first one 1 1, our answer, plus the second one 1. 1 plus the second one 1. It's all zeros. 1 plus the second one 1. What am I saying? Second, third one. 1 plus that one 1. 1 plus that one 1. 1 plus the last one 1. So this here is what will be our. This is where we started off. So I want that. So remember, you can be sometimes examiners and teachers try to be tricky. They may not necessarily ask you two numbers that are what that are easy to just move from one to the other. They can give you a number, let's say in decimal, so that you can show knowledge that you know you must first make it what call this binary before you can go to gray. Okay, they can give you they can ask you for gray code number and say they want your answer to be what? To be decimal or anything else. So you know gray can only go to binary first, then after binary you must then convert to whatever they asked you for. I don't think that's too much to ask. Yeah, I think it's easy enough. So I hope it was you had fun. I had fun. Just don't like when I make stupid mistakes, being careless and that. But anyway, otherwise, other than that, let's hope you, on the other hand, are covered.